Welcome back to the session. So we are pleased to have Golowich tell us about decoding quasi-cyclic quantum LDPC codes, please.
Thank you. Yeah, so this is joint work with Guruswami. And to start off, I'll just give a brief recap of quantum error correction with quantum LDPC codes. And in just the very generic setup, we have some number k of message qubits or logical qubits, which we encode into some larger number n of physical qubits, such that if some number, say up to d of our physical code qubits are corrupted, then we can perform some stabilizer measurements and recover our original message. And these stabilizer measurements are typically tensor products of Pauli operators acting on our physical qubits. So we might measure the tensor product of these three Pauli operators, these Pauli x's, some other Pauli x's, measure the tensor product of some Pauli z's, and so forth. And by combining all these measurement outcomes, we can hopefully infer what the error was and then correct it to recover the original message. And for an LDPC code, LDPC just means low density parity check. It just means all of our stabilizer measurements have constant weight. That means all of them just touch a constant number of physical code qubits. So we typically parameterize the performance of these codes with three parameters, n, k, d, which we list in brackets, where n is the code length, k is the number of logical qubits, and d measures the maximum number of errors that we can correct against. But there's also this additional important question that characterizes code performance, which is how can we efficiently decode against errors? In particular, how many errors can we correct against with an efficient polynomial time decoding algorithm? And this question will be the focus of this talk for some specific quantum LDPC codes of interest. So to specifically describe which codes we're looking at and also why we're looking at these codes, I'll first briefly describe one of the most popular paradigms for constructing quantum LDPC codes, which is as products of classical LDPC codes. So a classical LDPC code is just a set of bit strings defined by a constant degree graph called a Tanner graph. And rather than formally defining what a Tanner graph is, I'll just give the two examples that are most relevant in this talk and really that are most relevant to quantum error correction in general. So one is just a cycle graph, a sequence of vertices and edges going in a loop. And for a length n cycle, we actually get a classical code that's just a repetition code. It's just a code that takes a bit and repeats it n times. And on the other hand, we can also take an expander graph, which unlike the cycle is this kind of highly connected graph. It's still constant degree, but has edges going almost like a random configuration between all the different vertices. And if we take an expander graph and map it to a code, we get something that in this talk we'll call an expander code. And it actually has asymptotically good parameters in the classical regime. So it encodes a linear number of logical bits with linear distance, or it's able to correct a linear number of errors. So often we construct quantum LDPC codes by taking products of classical LDPC codes. And particularly if you just take two classical LDPC codes and take their product, you get a well-defined quantum LDPC code. And I'm intentionally being vague about what sort of product I mean here because there's actually multiple different types. There's tensor products, which are also called hypergraph or homological products. There's also things called balanced or lifted products. And I won't formally define these products in this talk, but we will kind of see how different products give different code parameters, and actually our decoding algorithms will apply to all of these different, both of these different types of products. Great. So which quantum LDPC codes can we decode efficiently? One catch here is that I'm focusing on asymptotic performance in this talk, so there's a lot of great work focusing on finite size instances. Here we're giving asymptotic algorithms with good asymptotic performance. It is a whole other question to kind of translate these algorithms to the practical regime. But on the one hand, we have the surface or the toric code, which has parameters. So for length n code, it encodes a constant number of logical qubits at distance roughly root n. And this code does have an efficient decoder, for instance, based on a minimum weight perfect matching algorithm. Now, on the other hand, we also have what I'll call in this talk quantum expander codes, which are these quantum codes that have constant rate or a linear number of logical qubits and dimension growing at least as roughly root n. I'm intentionally being vague with my terminology here because I'm allowing for kind of different classes of quantum codes based on expander graphs that fit in this paradigm. But all such codes can generally be decoded efficiently with a different algorithm, not a matching algorithm, but now something called like a small set flip algorithm, where you essentially greedily flip code qubits to try to reduce your syndrome error or your syndrome weight. Now the toric or the surface code is actually a product of classical repetition codes. You can see this visually because a classical repetition code corresponds to a cycle, and a torus is a product of 2 cycles, while a quantum expander code is a product of 2 classical expander codes. And these are kind of like 2 of the most commonly studied classes of quantum codes. On the one hand, there's the surface code, which seems to have a very good threshold in practice. It's been heavily optimized. On the other hand, quantum expander codes, like some of these even asymptotically good quantum LDPC codes, have very good asymptotic performance, though they seem to be a little more far off in the future in terms of practical applications. So one thing you might ask is, what happens if we take a product of 1 of each? Take a product of 1 expander code with 1 repetition code. We actually saw some products kind of this flavor in the previous talk. And if I were to draw this, it would probably look something like this. And these codes, the parameters actually interpolate between those of the toric or the surface code and those of quantum expander codes. The number of logical qubits will typically be up to root n, and the distance will be at least root n. And in this work, we're going to focus on decoding these types of products, these hybrid products between 1 expander code and 1 repetition code. So why are we studying these products? As I mentioned, kind of the product of 2 repetition codes and the product of 2 expander codes are both very well studied in the literature. Why kind of study this product of 1 of each? Well, it turns out that these products appear in various settings in the literature. So the first most direct motivation is the one I already mentioned, that in terms of parameters, rate, distance, locality, even spatial locality, these hybrid products interpolate between the parameters of the surface code and quantum expander codes. And each of these 2 classes of codes have some advantages and some disadvantages, so maybe you want to interpolate between them just for practical performance. Also, it turns out that these products of a classical expander code with a repetition code appear in some sort of lattice surgery or teleportation schemes. So it might be you actually really only care about storing data in a quantum expander code, and maybe you then want to teleport this data out into like a surface code to do some gates on it. There have been some schemes of this sort proposed in the past. And if you look carefully at these schemes, often they'll actually teleport between a quantum expander code and a surface code using an ancillary patch that looks kind of like a product of 1 of each. So just for this teleportation, these hybrid products can come up naturally. A third motivation is if we actually just look at nearly linear distance codes, so if we now want to take quantum LDPC codes with very large distance, very good error correction capabilities, there's been a beautiful line of works getting asymptotically good codes with completely optimal parameters in the asymptotic regime. But a few years ago, Panalev and Kalichev came up with a much more lightweight construction that obtained nearly linear distance codes with a logarithmic number of logical qubits and distance roughly n over log n. This was based on actually a balanced or a lifted product of a classical expander code with a classical repetition code. And this is actually very interesting because it's one of the only known lightweight constructions that we have for nearly linear distance quantum LDPC codes. And by lightweight, I mean that it doesn't need some of the heavy machinery called robust local codes or product expanding local codes that make some of the asymptotically good quantum LDPC constructions so difficult to bring to the practical regime. So these codes of them, these lifted products of an expander code and repetition code, are a very interesting potential direction to get towards very high distance practical codes, and one of our main results is a decoder for these codes. And a fourth motivation is that, probably in a direction very similar to the previous talk, but if we view the repetition code in this product as a time axis, then we can view the decoding problem for the product of an expander code and a repetition code as the problem of just decoding the expander code but when we're essentially decoding it over time from repeated noisy syndrome measurements. And this type of repeated measurements, it appears often in quantum computing. You can even ask questions about it in classical computing. Kind of our decoder fits naturally into this framework. Great, so I'll now state our main results for decoding these products, these hybrid products. We give polynomial time algorithms to decode both the hypergraph product of an expanded code and a repetition code, which has root n logical qubits in distance root n, and the lifted product of these codes, which has log n logical qubits in distance n over log n. And all of our decoding algorithms decode up to a linear number of adversarial errors with respect to the distance, which is an optimal number of adversarial errors. At a high level, our algorithm goes by reducing the quantum decoding problem to a classical decoding problem, actually in a black box manner. And this really uses this view of the repetition code as a time axis that I mentioned back on the motivation slide. So essentially, this view allows us to view the problem of performing quantum decoding with perfect syndrome measurements, which is the problem that the quantum decoding problem that we want to solve, and equate this problem with the problem of classical decoding, these classical expander codes with noisy syndrome measurements. Unfortunately, such classical decoders have already been known in the literature. For instance, like a greedy flip algorithm works. And so if we just apply these classical decoders in a black box manner, we almost directly get a decoder for hypergraph products of expander codes and repetition codes. It turns out that to decode the lifted products from Panalev and Kalichev, these nearly linear distance ones, we need to do some more work. It turns out that just directly applying this view doesn't quite get you all the way there for reasons I'll describe in a bit. But we can take these same general ideas and also decode the lifted products. Great, so I'll now try to give a visual depiction of our algorithm for hypergraph products. So here we assume there's at most root n adversarial errors that occur. And visually, so a hypergraph product looks like this if you haven't seen before. There's kind of two grids of qubits. There's some physical qubits here, and then a grid of z stabilizers and a grid of x stabilizers. You can see it's kind of like literally a product of an expander code, the Tanner graph of an expander code with the Tanner graph of a repetition code. And if we assume, say, for simplicity, that there were just 3 errors, one error up here, one here, and one here, then if we measure our z stabilizers, essentially some of them will be activated, which means that the measurement outcome was -1 instead of +1. And it turns out that this error will correspond to activating these 2 z stabilizers, while this error will correspond to activating these 2 down here, and this error down here will correspond to activating these 2. So essentially errors in this grid on the top right kind of will activate some z stabilizers in a column, whereas all the errors in this bottom left grid will each activate just a pair of adjacent z stabilizers. So the essence of our decoding algorithm is to try to isolate the effect of these errors in the top right grid, decode them, and then after we do that, we'll infer the errors down in this lower left grid. So first we'll actually compute prefix sums of the syndrome columns. So essentially we view every red dot here as a 1, every activated z stabilizer as a 1, every unactivated z stabilizer or every orange dot is a 0. And we just compute prefix sums across these columns. And you can see that since all of the errors down here caused 2 adjacent z stabilizers to activate, when we compute prefix sums, this essentially just shows up as like a single activation. Kind of will detect like a single 1 before these 2 errors like cancel each other, and we get zeros in the rest of the row. Whereas the z stabilizers that were activated from this error actually correspond to these entire rows of red dots. So essentially, after computing prefix sums, we can apply our classical noisy syndrome decoder to each column, and then we compute pairwise differences essentially to revert the action of the prefix sums. Pairwise differences are the inverse of prefix sums. And after we do this, we've hopefully recovered the errors in this top right grid. So then once we've kind of inferred what's up here, so then we're just left with the errors down here, and for this purpose, we just match whatever remaining syndrome errors we have. So for instance, we see that there's 2 adjacent syndrome errors, or there's 2 adjacent activated stabilizers here, so we infer that there was an error here, and so forth. So yeah, I guess just to summarize, at a high level, we're really computing prefix sums to isolate the effect of errors in this top right grid. We use our classical decoder to infer exactly what these errors were. Then we uncompute the prefix sums, and then use a basic matching algorithm to infer the errors down in this lower left grid. Great. So for the lifted product, we at a high level use a similar algorithm, but if we try to do this, we can see something will go wrong pretty quickly. Because now our code has nearly linear distance n over log n, and so we want to be able to correct against a nearly linear number of errors. But if we have more than root n errors occurring, and we take prefix sums of more than root n columns, this could potentially accumulate to more than n errors, which would actually overload our classical decoder. And this is kind of why in the hypergraph product case, we were not able to decode more than root n errors. So our solution to this is actually to first try to decode based on very short prefix sums. We take prefix sums of just like constant length and try to do at least some amount of decoding, infer some of the errors that occurred. And then we kind of iteratively increase the prefix sum length, repeatedly do a little more decoding, infer a few more of the errors, and so forth, just bouncing back and forth between taking longer prefix sums to decode even more errors, which allows us to take even longer prefix sums without ever overloading our classical decoder that we're applying at each step in a black box manner. So that's kind of a high level, at least, description of how we adapt this hypergraph product decoder to the lifted product. The analysis is a bit involved, but these are the main ideas. So to wrap up, I'll just describe a couple of future directions. So the first is whether we can handle a linear number of random errors. It turns out that the algorithm I've described, it is optimal against adversarial errors in that it corrects up to a linear number of adversarial errors with respect to the code distance. But we haven't actually considered a linear number of random errors where we have like some constant error probability. So another way of saying that is like we haven't given a decoder that would maybe have a threshold against random IAD noise. And this actually is often this type of random decoder follows from an adversarial decoder basically by using some like percolation arguments, but this is a bit trickier in our setting because our decoder isn't local. It's actually more of a global algorithm, which I think makes this an even more interesting question. There's also the question of handling measurement errors or noisy syndromes. So to decode our quantum codes, we assumed black box access to a classical decoder that worked against classical noisy syndromes, but our entire quantum decoder actually assumed that the original quantum syndromes were perfect. So it would be interesting and also important in practice if you could adapt our algorithm to handle such syndrome errors. There's also the question of whether we can decode our generalize our algorithm to more codes. So right now we're looking at these products of like one repetition code and one expander code, which, as I mentioned, appear in many different settings in the literature, but it's also natural to ask whether we could extend this to, for instance, more codes that maybe still have like a large cyclic group symmetry or some sort of similar structure. We could also ask about extending it to like higher dimensional products. Maybe we take the product of a quantum expander code with a repetition code, which you can also think of as like a product of two classical expander codes with one classical repetition code. And finally, there's the question of finite size performance, whether our algorithm helps in practice for these types of quantum LDPC codes. So that's all I've got. Thank you.
So why do you title your talk Quasi-Cyclic Codes?
Right, so I think I guess I didn't phrase it in this way, but this step where we're taking prefix sums in the decoder, one way you can think of that is really leveraging the cyclic symmetry of the repetition code. We're kind of taking we're using the cyclic group action to take shifts of our codes and adding these syndromes together. And that's how we get like this cancellation from the errors in like the lower left corner, which lets us isolate the errors in the top right corner. So in some sense, you can see the key idea in our decoding algorithm is to leverage like the quasi-cyclic nature of the codes.
What's the complexity of the algorithm?
Oh yeah, so the hypergraph product algorithm, hypergraph product decoder is roughly linear. I guess if you wanted to, so it turns out like there's a bit of a complication. You need to kind of choose a random starting point or try all starting points. So it's like roughly linear time if you allow randomized algorithm, and like n to the 3 halves if you really want a deterministic one. For the lifted product, it's roughly n squared, or n squared, n to the 2 plus epsilon, something like that.
Hi, nice talk. So could you go to the slide with the prefix, like the decoding stuff, prefix sums? Yeah, so here, if I have, in the top right block, if I have 2 errors that are right next to each other, then don't I get kind of 2 pairs of z-stabilizer errors, which then looks exactly like I had 2 errors on the lower left block?
Yes.
And then it's a
Yes.
failure of the decoder, or what? Because then it looks like you have 2 errors that you can't distinguish between. I mean, they have the same weight, or
Exactly, yeah. And it turns out that these 2 errors differ by a stabilizer. So if you identify and correct either one, then it's as if you instead corrected the other one and then multiplied by a stabilizer. But multiplying by a stabilizer actually does nothing to your code.
okay, great, thanks.
That's a great talk. If you take hypergraph product of 2 expander codes, you explain you obtain a contact expander code, and this is decodable. And your results shows that now we can take expander code and cyclic code, and still we can decode. And is your analysis implies something that in terms of rate, still expander code is better? Does your analysis provide some advantage or disadvantage? Maybe compare these to different construction in terms of like in some other like.
I see, like
property.
any parameter improvements?
Yes.
Yeah, so asymptotically, I think these types of products will, I don't know of any setting where they're better. I'd say, like in terms of being like a lightweight construction, like, yeah, I think so. One of it is for the, like if you want nearly linear distance, this is like the only construction we know that you can kind of write down explicitly without some like really messy local object. And there's also hope that if you apply it to like this view of kind of decoding from repeated syndrome measurements, even like replace the classical expander code here with a quantum expander code, this might be helpful for certain tasks like maybe state preparation, where you essentially want to do repeated syndrome measurements and run some decoder.
Thanks for the talk. Do you have any numerical results or comparison with existing algorithms?
Sorry, we don't at this point, but it's a great question.
I have a question. So you said you like to extend it to measurement errors as well, and so have you considered data syndrome codes? Data syndrome codes? I mean, so
No.
there's a field called data syndrome codes that, well, aims to address this problem. So maybe you've thought about that.
I see. I haven't, but thank you. We'll have to look into it.
Are there any further questions? If not, let's thank the speaker again.